Today we're going to look at time dilation. Time dilation is one of the first effects that we'll be looking at of the special theory of relativity, namely those Einstein's first two postulates that the laws of physics are the same in all inertial reference frames and that the speed of light doesn't vary across reference frames. So if we just have a look and consider a train carriage moving at some velocity v with a clock inside that uses light pulses to measure time. So a light pulse is emitted from the emitter here, it's reflected off the ceiling and is collected back into the sensor. It's sensed the time, and the time difference is measured. So we can see that we can use just the normal distance formula to determine exactly what distance this space is going to be based on the time that is measured. So if the time measured is t0 inside here, we can see that the time is going to be measured relating to the distance and the speed of light that the light moves at. And that c, that speed of light, once again is constant, approximately 3 times 10 to the 8 meters per second. Now, and that's for an inside observer, someone who is sitting inside the carriage observing it. They're not aware of the motion of the carriage, the velocity, the light just seems to move up and down. If we have a look at an outside observer, before looking at the mathematics too much about it, if we have a look at the outside observer, someone stationary on the side of the tracks, they're looking and they're stationary with relation to the movement of the train carriage. We can see that they would see the light being emitted, being reflected later as the carriage has moved, and being detected back at the detector. And already we can see that the actual distance the light has to travel is going to be longer. There's going to be a larger distance that the light has to travel for the stationary observer compared to the observer inside the carriage. And remember, the speed of light doesn't change. The speed of light doesn't change, so the velocity of the light is going to remain the same. The distance is getting greater. That means the time must also be greater. In order for if our space is getting larger, the time must get larger as well. They are in direct proportion to each other to make sure that the speed c remains constant, remains the same. So we can, just looking at the maths here, we can measure what the difference in the distances, the difference in the distance, the difference in space, and also the difference in time. So we've called the time for the inside observer t0, as in that's t0. That's the one that the inside observer is the time that the inside observer is experiencing, and the outside stationary observer, they're going to observe a different time, and we're going to call that just t without the zero notation next to it. So if we just look at the inside observer for the moment, we can see that the distance that the light is going to traverse, because it's being emitted and then reflected back, is going to be c, speed of light, times t0, and then divided by 2 because it's going up and back. Okay, so it's only doing half of that, or that distance, it's doing twice that journey. So we remember that speed equals distance over time. So here we've got speed, we've got time, and we've got distance. So if we rearrange speed equals distance over time, we get distance equals speed times time. The divide by 2, once again, is because it does half that distance, or it does twice the distance. It goes up and then it goes back. So d is going to be a half of the total time that it takes to go there and back. So looking at an outside observer, a stationary observer, the light is emitted from the emitter, it's reflected off the ceiling, and then is detected back in the detector. And the time it takes for that to occur is going to be t, without the zero notation. Now, during this time, the carriage has moved along, so that the distance between where the light is emitted from and where it is detected is this distance here. Once again, speed is distance over time, but we're not looking at the speed of light in this case because the difference in distance here is related to the carriage, the movement of the carriage. Because the carriage has been moving at some velocity v, that is what has caused this change in displacement as it's moving to the left and right. So we've called this displacement s, and that's equal to vt. So velocity, the velocity of the carriage, how quickly it's moving, multiplied by t, the time that the stationary observer is observing. Now the distance that the light travels along one of these axes, the whole thing is going to be the speed of light times the time it takes. That's going to be the distance there. Once again, just because speed equals distance times time, that means the distance is going to be speed times time. So the speed of light, which is constant, c, times the time that is observed. So we can see mathematically that this ct over 2 is going to be this length here because it's half of the total distance that the light covers. It goes up this amount here and then back. And you can see that we actually have a right angle triangle that's made, by half of that distance, half of the distance that the carriage has moved. And one side length is a half of the distance that the light has travelled according to this stationary observer. And this side here is a half of the distance, that the light has travelled for the inside observer. That length there is that here. So we've got L being this side here, a half of this value S here, and D here, this value here. Okay, and Einstein had a look at this Pythagorean triangle and just used the Pythagoras' theorem on it to determine a relationship between the time that's observed from the outside observer and the time that's observed by the observer that's inside the carriage. So once again, here is that triangle that we had. Here, the distance along here is ct0 over 2. So that's just the speed of light times the time it took to get back, divided by 2 because it's half of that time. Here we've got ct, so this is the distance the light travelled from the outside observer, divided by 2 because it was then coming back down here to be detected by the detector. And here, along this side, we've got the distance relating to the velocity of the carriage, the movement of the carriage, as viewed by the outside observer. So we can just use Pythagoras' theorem that c squared, the hypotenuse squared, equals the square of this side plus the square of that side to give a relationship between the different sides. And we can do some very simple algebra on it. Here, multiplying every term by 4. Here we have divided every term by c squared. Then here we have we've subtracted v squared t squared over c squared from both sides and rearranged it slightly. And here we have removed the common term of t squared outside the brackets to give the 1 minus v squared on c squared. Taking the square of both sides, the square root, of both sides yields t0 equals t times the square root of 1 minus v squared on c squared. So you can see here, this is the time that's measured by the inside observer, and this is the time that's measured by the outside stationary observer. So I can introduce now to you this gamma. Is called the Lorentz factor, and the gamma is equal to this 1 divided by the square root of 1 minus v squared on c squared. And this Lorentz factor comes up a lot in special relativity because it's not just time that will be different for both observers. There are other aspects of special relativity that use this Lorentz factor to compare what two observers will witness and two observers will observe. So for a very simple relationship, a relationship between t0 and t, we see that t0 is equal to t divided by the Lorentz factor gamma. Now, one of the most confusing things relating to this effect that we see, this effect of special relativity, time dilation, is which is the proper time, which is t0 and which is t. And the relationship between them is challenging, because when we have a look at, if I was the inside observer in the carriage looking out, it would appear to me that the outside observer was moving away from me at the same velocity that the stationary observer sees the train moving away from him, just in an opposite direction. So which is proper time and which is relativistic time? So proper time is defined is this value t0 that we found. That's the time measured in the reference frame where the two events occur in the same place. We saw the light was being emitted from the same space. It was emitted from the same space and it was retrieved to the same space. That was as the inside observer saw it. It went up, straight up and straight back down again. The proper time is always going to be less than the relativistic time. The reason for that we could see is because with our measuring our light pulse, the time that was taken for the light pulse to move forward and back by the light clock was much less. The distance was much less for that clock than for the clock as appearing to the outside stationary observer. The time was much longer there. So the proper time here, t0, is much less, is less than relativistic time. Relativistic time, denoted with t without the 0, is time measured in the reference frame where the two events occur in different places. So we saw that the train carriage was initially over here, and the observer saw the train carriage move and saw the light be emitted from the clock in one place and be received by the clock in another place, in two different places, two different spaces. Okay, so if we've got an example here, we've got a rocket travelling from Earth to Gliese 581c, the third planet from the star Gliese 581. The Earth-Gliese reference frame is going to measure relativistic time. They're going to be measuring relativistic time because they're going to be measuring the time on Earth. Maybe it's 12 p.m. on August the 3rd, and then the time whenever the rocket gets to Gliese 581c, and that might be that'll be using a different clock and a different calendar, presumably. So the time that's measured on the actual spaceship as it's moving is going to be the same clock. The clock is not moving on the spaceship. Okay, and so proper time will be measured on there. It'll be measured in the same place on the spaceship as it's leaving Earth, and at the spaceship as it reaches Gliese 581c. So despite the fact it's travelling with some velocity, the Earth and Gliese 581c will measure relativistic time, and proper time will be measured by the rocket in this example. So two examples to have a look at. Firstly, determining the velocity a proton needs to have to travel at half the time it would take to spin 360 degrees compared to at rest. So we're taking rest time. Rest is proper time for the proton, and relativistic time is the time that's going to be measured in the laboratory. So let's have a look at that example here first. So we've taken the time observed in the laboratory. The time is going to be twice the amount that it was if it was at rest, to travel to half the time it would take to spin 360 degrees. Yeah. So if it was at rest, we would be measuring it to be going at half the speed. So the ratio between t0 and t is going to be 1/2, 0.5. So in order for that to occur, we can just do a little bit of algebra on it here, and manipulate these equations, squaring both sides of the equation, and subtracting subtracting 0.5 squared and subtracting v squared on c squared from both sides and getting this, yielding this equation. We can then multiply both sides by c squared. We get v squared equals 1 minus 0.5 squared times c squared, and then we can find the square root of both sides. So the square root of this term here multiplied by c. So that velocity relating to c is going to be 0.87 c. Okay, we can represent velocities with respect to c. C is such a large number, and it's a constant, and often velocities that are large, so large, we're talking about, are very closely related to c. So we represent them as a component to c, very much like radii or anything relating to circles is often related to pi, rather than obtaining an actual figure in order to not worry about all of the decimal places and all of the significant figures that would be lumped in with that. So question 2 here, analyse whether or not it would be viable to send humans to the next nearest star to Earth. So our nearest star is the Sun, but the next nearest star is about 4.5 light years away. To Earth if it took 19,000 years from Earth's reference frame at a velocity of 0.0002 c. Okay, so we're travelling at a very small percentage of the speed of light, and let's have a look at exactly over this time frame. Let's have a look at the actual time dilation effect of that. So in the Earth's reference frame, t is going to be 19,000 years. The velocity is 0.0002 c, and we're looking to find the proper time that's going to be aboard the spaceship. So proper time is going to be t multiplied by the inverse of the Lorentz factor here. So just substituting in. If we substitute in our velocity here, because it's represented with c, the square of the velocity is going to be 0.0002 squared c squared, and the c squareds cancel out. So this is a trick that will probably make calculations a bit easier. Often the speed of light term will be able to be cancelled with other terms in equations, especially things like the Lorentz, and anytime the Lorentz factor is present. So you can just see just how insignificant the Lorentz factor is going to come out as in this instance with this such low velocity, and we can see that the actual proper time that it's going to take the travellers on this spaceship is going to be 18,999.9996 years. It's a difference of about 3.3 hours. So at this very low velocity, the time dilation, it's a relatively low velocity, it's still many thousands of kilometres per hour, but because it's not anywhere near the speed of light, the actual effect that the time dilation has is very, very low. In fact, it's 3.3 hours in 19,000 years is a very, very small percentage. So this amount of time is 60 human generations. The time dilation effects are negligible unless you've got a large population on this ship. It's going to be very, very difficult to maintain the 60 human generations needed in order to travel to this 4.5 light years away star. If you were to travel at a larger velocity, perhaps there would be less generations, it would be more viable. But as far as travelling at this relatively low velocity and it taking that length of time to reach this star, it is not a viable not a viable situation for space travel.